I'm only going to talk very briefly on this section, the periodic table, because I'm hoping a lot of this is review. So I'm going to assign this as self-study. Read it, see if you have any questions, make note of your questions. Just a little joke here. What I am going to show you on the next slide isn't in your pre-lecture notes in this order if you're following along there. But I put it here so I have something to point to. Make sure you're comfortable with all the terminology of the periodic table, that you know what a row is, what a period is, what a group is, and the names of some particular groups. What's this group called? What's that group called? What are these? Make sure you know what this group is called, and that you know the significance of the dividing line that's shown more dark over here. I'm not going to review those, not a good use of our time together, but do read that section as always and make notes of any surprises so that you can ask me. The main point of this video is to distinguish between molecular or synonymously covalent and ionic compounds. We need to distinguish for a couple of reasons. One is fundamentally that their behavior is different and we need to recognize them. But the last section in chapter 2 is on naming compounds, and we have to be able to distinguish whether they're ionic or covalent in order to do that. So the big picture is that when atoms are not stable by themselves, they combine with other atoms to make compounds. Even when they are stable by themselves, sometimes you can get them to make compounds. The big idea in all of chemistry is that opposite charges attract. Atoms are made up of charged particles, protons and electrons, so they can interact with other atoms, and the way they're held to other atoms distinguishes whether they're covalent or ionic compounds. So first, let's start with covalent compounds. We recognize those when we look at the elements. From the positions in the periodic table, we recognize a covalent compound when we see a nonmetal combined with a nonmetal. Oops, nonmetal, very funny. With a nonmetal combined with a nonmetal. And what happens is that one nonmetal atom wants to share electrons with the other atom. So here's an example from an earlier slide, and I said it was vinegar the last time and corrected myself. I think I will say that molecular formula, C2H4O2, is the formula for acetic acid, which is the solute in vinegar. What I can see when I look at the structural formula or the molecular formula is that there are carbon, hydrogens, and oxygens. Those are all nonmetals. And you know how to know that from its position in the periodic table. The metals are on the left of the zigzag dividing line, and the nonmetals are on the right. Hydrogen's an exception. Even though it's on the left, it usually behaves as a nonmetal. The nonmetal atoms in a covalent compound are held together by covalent bonds. And a covalent bond is just a shared pair of electrons between the atoms. I'm going to say more explicitly that it's a shared pair of electrons between nonmetal atoms. Usually metals don't make these shared pairs. And when we have a group of atoms held together by covalent bonds, that stick represents a shared pair of electrons or a covalent bond. A group of atoms held together by covalent bonds is called a molecule. Group of nonmetal atoms held together by covalent bonds. So this picture of a model accompanied by a structural formula, accompanied by a molecular formula, those are all representations of a molecule of water. In contrast to the covalent compounds made up of molecules, we can look at ionic compounds. And ionic compounds, by definition, are made up of, a lot of whoops this morning. An ionic compound is made up of ions, in other words, made up of charged particles. The way you're going to recognize an ionic compound from its formula is that it's got a metal combined with a nonmetal. Metal and nonmetal, that's ionic. That's in contrast with the two nonmetals in a covalent compound, two or more nonmetals in a covalent compound. So I've got an example of my favorite ionic compound, sodium chloride, or table salt, NaCl. In that formula, I don't see any charges. We don't include the charges when we put the formula of an ionic compound together. But I recognize that sodium is on the left-hand side of the periodic table. On the left of that zigzag dividing line, that's a metal, and chlorine's on the right-hand side. So because I have a metal and non-metal together, this is an ionic compound. And we'll review how I know that the charge on the sodium ion in the compound is 1+, and the charge on the chloride is -1. That's coming for now. Now, sodium doesn't always have a positive charge in it. It's only got a positive charge when it's an ion, when it's in an ionic compound with a metal and a non-metal together. Lest you say I'm lying to you later, I'll make one little change here. I'll say that it's usually a metal in an ionic compound. But more generally, an ionic compound contains ions, positive ions and negative ions, and it's just that the most common positive ions we know come from metals. What I've got there is a picture of an ionic compound, sodium chloride, and there's two kinds of pictures here. I think this A is a more realistic one, and it's got the sodium ions sitting next to the chloride ions in a repeating pattern. Little sodiums, bigger chlorides. We'll review later in the semester how I know which is the big one and which one is the small one. So what holds that ionic compound together is the attraction between those oppositely charged ions. And that's going to be a big theme in all of chemistry. What holds anything together is opposite charges attracting. Sometimes you'll see models of sodium chloride with this form that shows a line between the ions. That's kind of misleading. That kind of suggests that there's a covalent bond between them, and there is not. There are no shared electrons in there. So what I'm going to show you with my model here of sodium chloride, again, it's got these metal bars that are imaginary, holding the sodium near the chloride, but that's just to hold my physical model together. There are no bonds between them. What's holding it together is the attraction between one ion and another ion. Another thing I want to show you with my model is that there is no particular unit that is sodium chloride. This sodium is attracted to this chloride and to that chloride and to that chloride and to that chloride. So the bonding in an ionic compound, or the attractions in an ionic compound, are non-directional. Now let's use the sodium chloride example to remind ourselves of a few things. I said sodium's only charged if it's in an ionic compound, if it's with a nonmetal. But if ions form, then the metal loses electrons and becomes a positively charged ion. And the name for a positively charged ion is a cation. Positively charged ion, cation. The nonmetal gains electrons and becomes a negatively charged ion. And you know the fancy name for a negatively charged ion. That is an anion. So as I've told you, the oppositely charged ions attract each other, and we call that an attraction an ionic bond, an attraction between oppositely charged ions. Whoops, little technical glitch there. Attraction between oppositely charged ions. I kind of wish they hadn't called it an ionic bond, because for some people, bond implies shared electrons. There are no shared electrons. There are no covalent bonds between the ions in an ionic compound. And what that means is that there's no molecules in an ionic compound. There's no such thing as a salt molecule. I showed you with the model that each chloride is simultaneously attracted to a number of different sodium ions. Each sodium ion is simultaneously attracted to a number of chloride ions. That's very different from what happens in a molecule like for water. In water, this oxygen is attracted to these hydrogens only, covalently bonded to those. And it's easy to distinguish that, from another water molecule. This oxygen only to those hydrogens, this oxygen only attracted to those hydrogens. So we can't talk about molecules in ionic compounds. Instead, we talk about a formula unit, which is the smallest repeating unit of an ionic compound. And for some of you, that may be a brand new thing. A lot of this course has been reviewed so far, but that may be new. No molecules in an ionic compound. We talk about formula units instead. Maybe I can express it in another way to make it even clearer. The formula unit is the amount of the substance represented by the formula. So for sodium chloride, a formula unit would have one sodium ion and one chloride ion, because that's the amount represented by the formula. But if I had calcium chloride, say, a formula unit of calcium chloride would have one calcium ion and two chloride ions in the formula unit. In the ionic compound at large, of course, there would be many, many of those ions, but a formula unit represents the small amount represented by the formula. Now, I wrote on those pictures the charges on the ions. The last thing I want to do in this section is remind you how you know what the charge is on an ion. Now, remember, this is only talking about ions, things with charges on them, things in an ionic compound, metal and nonmetal together. The way to find the charge depends on which part of the periodic table the element comes from. So the easiest ones to look at first are the main group elements, the ones in the tall columns. Those form charges so that they are isoelectronic with the nearest noble gas. And you scholars of language know what that means. Iso means the same as, so isoelectronic means the same number of electrons as the nearest noble gas. So for the example of calcium, in the calcium chloride I just gave you, in the compound calcium chloride, what is the charge on calcium? Well, here's calcium. The nearest noble gas is argon. The atomic number gives the number of protons in the nucleus, but in a neutral atom, there's the same number of electrons. So a neutral argon atom has 18 electrons. Calcium is going to become an ion with the same number of electrons as argon. Calcium is going to end up with 18 electrons in the ion. It started with 20 in the neutral atom. It has to lose 2 electrons to end up with 18 electrons. And remember, we're losing 2 negatively charged electrons, so the calcium becomes 2+. Here's another example. If I had phosphorus in a compound, what would its charge be? If you need to pause me and figure it out, go ahead. Here's phosphorus. Its nearest noble gas is also argon. In a neutral atom, phosphorus has 15 electrons to match the 15 protons. To get 18 electrons, it's going to have to gain 3 more electrons. In other words, a phosphide ion has a charge of -3. And just so we get it right the first time, when I write the charge, notice that the number goes first and the sign goes second. That's the convention that IUPAC accepts. You may remember a shortcut. You may see that calcium, I had to go 1, 2 back to get to the nearest noble gas. So calcium is +2. And for phosphorus, I'd have to go, 1, 2, 3 to get to the nearest noble gas. That's why it's 3-. But although it's good to have that for quick recall, I hope you know the deeper reason why. It's so easy to forget the facts if you don't know why the things happen the way they do. So I'm glad that you know that that's what happens in the ionic compound to make those ions isoelectronic with the nearest noble gas. But careful, that's not really a very deep why either. Why does it want to be isoelectronic with the nearest noble gas? We'll find out later. And I'm sorry at this early point in the course, I'm going to have to give you some authoritative knowledge just so we get a working vocabulary together. But as soon as I can, I want you to know why everything happens so that you're not relying on memorizing anything. All right, that's it for the main group elements. Now we're going to look at the transition group elements, which are the guys in this short column here. They're a little more challenging because transition metal ions can have more than one charge. So if I look at iron, for example, Fe, what is its charge? Well, if I just had an iron nail, pure elemental iron, it wouldn't have any charge at all. It wouldn't be an ion because it's not in an ionic compound with a nonmetal. Elemental iron has no charge. But I know from experience that if it is in an ionic compound, sometimes iron is 2+ and sometimes iron is 3+. We would call those iron 2 or iron 3. Don't worry, the context will tell you which one you're dealing with. You don't have to anticipate it. I will say for fun that most of the transition metals can be 2+, but can be other charges as well. Different transition metals have different preferred charges, and that's another thing we'll learn in the future, and it will make sense. One last thing before I end this video. This periodic table is the one that I will provide you on quizzes, on tests, on exams, and you'll notice that it has only 3 entries in each block of the periodic table: the atomic number, the element symbol, and the atomic mass on the bottom. I am not going to give you any more than that because I don't want you thinking that you need more than that. We don't memorize periodic tables. It will always be provided, but you can learn to use it in a way that you don't need the more detailed tables you sometimes see. So for example, you don't need it written on that table to how to know what the charge is. You just been refreshed on how to figure that out. All right, let's call that a break for this video, and we'll come back and look at how to name compounds.